Think about how many devices around you rely on batteries. Phones, laptops, even electric cars. But what actually makes batteries work? At the heart of it all is electron transfer. Electrons flowing from one substance to another in a way that releases energy. Understanding why electrons move and how we can predict that movement allows us to design better batteries and more efficient energy storage systems. And it all comes down to the properties of different materials and how they interact with electrons. Esto es Real Chem. The spontaneous direction of electron flow is determined by the properties of the materials involved. Specifically, which one's more likely to give up electrons and which one's more likely to receive them. In other words, which substance likes electrons more. That's what it's all about. Some materials are much eager to gain electrons than others. To see how this plays out, let's compare two common metal ions. Copper ions have more positive standard reduction potential, E0, than zinc ions. This means that copper likes gaining electrons more than zinc does. The Daniell cell, one of the first batteries ever built, took advantage of this difference. Since zinc likes electron less than copper does, the spontaneous direction of electron flow is from zinc to copper. We can describe this process by combining the reactions from our table. Electrons are leaving the zinc metal, so we reverse the reaction for zinc so that electrons are products. Electrons are going to the copper ions, so we keep their copper reaction as written, with electrons as reactants. When we add up these two half reactions together, the electrons cancel out, leaving us with a balanced overall reaction that describes what happens as the battery discharges. Now that we have the overall reaction, the next question is, what is the voltage of the battery? Each reaction in the table has a standard reduction potential. Since we reverse the reaction for zinc, we also need to reverse the sign of its standard reduction potential. The reaction for copper was kept as written, so we leave its standard reduction potential unchanged. To find the total voltage, we add the two standard reduction potential values together. If the sum is positive, it tells us that the reaction is spontaneous, meaning the battery can provide energy. For the Daniell cell, adding these values gives us a positive voltage, confirming that electrons flow from zinc to copper in a way that is spontaneous and releases usable energy. Now let's add silver to our table. Silver likes electrons even more than copper does, so electrons will spontaneously flow from copper to silver. Let's combine the reactions from our table to describe this. Electrons are leaving the copper, so we reverse the reaction to show electrons as products. Silver is gaining electrons, so we leave its reaction as written, with electrons as reactants. But there's a problem. The electrons don't cancel out. Each silver ion only takes one electron, while each copper atom loses two. To balance the reaction, we double the silver reaction so that the electrons cancel when we sum the reactions. Now, let's consider the potential for the overall reaction. Remember, when we reverse a reaction, we also need to reverse the sign of its standard reduction potential. Since we flipped the copper reaction, we must change the sign. But now there's something new. We doubled the silver reaction. Shouldn't we double its standard reduction potential value? The answer is no. Standard reduction potentials are defined per electron transferred. So no matter how many times the reaction happens, the energy difference per electron stays the same. Adding the adjusted standard reduction potential values gives us the total voltage of this reaction. The positive value confirms that the electrons move spontaneously from copper to silver, just like they did from zinc to copper. Understanding these values allows us to predict which reactions will generate energy and which will require energy input. By understanding which substances want electrons more, we can predict which reactions will release energy and design systems that put that energy to use. But spontaneous electron flow isn't just useful in batteries. It plays a role in corrosion, industrial metal refining, and even biological systems. Wherever electrons move, chemistry follows, and understanding its movement helps us control and harness it.